Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're gonna talk about another mission, Cassini-Huygens mission. So let's dive right into it. Now, first, before I dive deep into this, you have to understand these missions are huge, as in they took decades to complete. So the amount of information that is coming out of these kind of missions are huge. So I would urge you, once you have watched this video, please go into NASA's timeline so you get a complete overall pictures. It's not something that I can compress into a video. However, let's talk about the things that I can talk about. So what was the target? Simplifying this way, when we had Voyager mission, they were like a graduation system. This puppy was a post-graduation. Basically, okay, we got the gas giant overall picture, how they are, how they operate. Let's go study one of them closely. Now, this puppy was targeted for Saturn system, specifically Saturn's moon, because Voyager flat out provided proof that those moons are interesting, aka some of them have atmosphere, some of them have water bodies and all that jazz. So it was like, okay, we have interest, point of interest, let's focus on that. And this was also supposed to land on Titan. Then it was launched in 15 October 97. It was a joint mission between four core parties. One of them was NASA, obviously. Then Jet Propulsion Lab, which made the whole spacecraft. Then it was European Space Agency plus Italian Space Agency. And these two people were directly responsible for the Huygens part of the mission. So what was the instrument? Now, it had similar amounts of instrument, but there was a very specific development in the instrument industry, simply because this was like 20 years after Voyager. So it had 12 total instruments. 4 were optical based, basically, your RGB, infrared, ultraviolet, and all that jazz. Then you had 6 particle wave magnetic fields and all that jazz. Then 2 radar based. Now that's the most important part. The moment you see this white dish, that is what it's talking about. It's a radar system, and because of this kind of very heavy instrument suite, it was able to become first of many things. Basically, like, it became the first thing to actually image Titan's lake, so to say, simply because Titan's atmosphere is very dense. Like, you cannot see outside of it. So it's almost like a Venus in that regard. It's like atmosphere flat out blocks it. So you have to use radar system. Nothing else can penetrate it. So radar was very important. Like, okay, radar had to work, otherwise this whole mission would not work. So it became the first. So now whenever you see image, there is like, people are absolutely sure that there are lakes on the Titan. That's the reason, because before this, that was like, spectral analysis, like we think like this. No, this time we got the evidence, mathematically proven. Then another aspect, on one of the moon, Enceladus, it had basically icy core out of it. Basically everything was just ice. We know for a fact, like we can see it, and it's not like, okay, we can only see one side. Like, we took orbits around it, and because of its motion, it was very easily observed. But how the mathematically we assumed it had basically subsurface ocean, aka water, liquid water in normal form inside the surface. The reason for that was, like, even though it should be frozen, because of the gravitational energy pumped into it, it should be molten state. Now again, one of the volcano literally blew up in the same place, and it because of the low gravity, it plumed out a very very far. It's like very far, and the probe directly went through it. During this time, it flat out analyzed, okay, this is water, this is salty water, this has this and that. Like, this became the first. Like, before this we had mathematical models. Okay, it should have subsurface ocean. After this, like, dude, this is subsurface ocean. Like, we got this. Like, absolute proof. It's like, it's water, it's salty, it has these kind of things. Flat out amazing work there. Another interesting part is the polar region. The polar region is a hexagonal vortex. How the heck? But again, there are many mathematical proof about that. But it's like, we are still fine tuning it, because this has to do something with how ice crystals always have a 6 side or something like that. It's like they're still working on it, like what exact fine tuned detail. But we got the idea, and it was quite unique. Before this, everybody was like, you can see CGs before this era, and it was like everybody had like swirling top. Now everybody has to have hexagonal top. So it became a very successful mission, because the original target was like 8 years. After that, because the equipment was working and they were discovering more and new things, they're like, let's increase it. Let's increase it. So they kept increasing it. So it was very successful in that regard. Now, power and propulsion. Whenever you are talking about a mission, you have to have a way to power those instruments. On top of that, you have to have a way to aim it. You cannot have a radar that is pointer somewhere else in the space. You have to point it exactly. I'm studying this part. Or whenever you are making a quote unquote flyby, you have to constantly readjust your aiming system. So power and propulsion are very important. So power wise, they knew, because of the radar requirement, they had to have a lot of oomph, lot of power on top. So the easiest way was RTGs. They put 3 RTGs, same same as Voyager, and you can see like this was big puppies. And then they had two independent rocket systems because of the way this mission was designed. It's supposed to land, quote unquote. So they had to find a way where they can, like, insert into orbit and exit the orbit on their will. So for that reason, they cannot rely on thrusters. Thrusters gives you aiming accuracy. It's like, okay, I'm just making a flyby, I'm just gonna aim my antenna here and my equipment's here, awesome, no problem. But if you have to slow down so you can enter an orbit, or then speed up so you can leave the orbit, that is a completely different requirement. To handle that, they had two independent systems. Primary system for aiming and fine-tuning was 16 hydrogen system. Now when I say 16, you have to understand half of them were needed, because it was each thruster pack was designed with dual redundancy. Like this, they had two of them. Every place, every location had two of them. So no matter what happens, those systems will work. And this was like 1 Newton, but this was mainly there for aiming the antenna, aiming the dish, aiming the radar, and all that jazz. Then you had main engine, like, and if you see why the heck it has two main engine, well, it only needed one, but because of the importance of the mission, they put another engine on top of that. And the very interesting thing is, in NASA's main documentary, it said main engine, backup main engine. So this was not thruster backup, like this was a completely capable. However, they never needed to use it. The primary engine kept working, and this primary engine was a bipropellant system, so it had more thrust, more oomph into it, and it was utilizing nitrogen tetroxide, NTO, and monomethyl hydrazine, MH, basically MMH. So this was the main power and propulsion equipment aspect of this. Then we come to the Huygens, basically the Italian and European agencies' contribution. Now this was specifically designed for landing on Saturn's moon. Now because the atmosphere is so thick, they flat out realized that it will remain in the atmosphere a very long time. Basically it will enter it will deploy parachute, but it will not be like, okay, 8 minutes we landed. It will be hours. So to utilize that advantage, they put a gas sniffer, so to say, into it. So they can literally siphon atmosphere from upper atmosphere, figure it out what the heck is there, middle atmosphere, then almost before landing, and then that way they can get a thorough analysis of different atmospheric layer or whatever the composition is, and it was very successful. However, you have to understand that this had chemical batteries into it, so it was never intended to be there like, okay, it's gonna land and it's gonna continuously send data. Flat out, it was not meant to do that. And its antennas were so weak that it could not directly target Earth, so it had to target the orbiter, so to say, and that also backfired simply because it had two antennas as a redundant backup system, and it was designed in such a way that half of data would be sent in one way, another would be sent another way. One half worked, but another half did not, so they ended up in a scenario where it's like only half of the photographs came back, and other instruments were also not working. Like this was successful because again it became the only thing so far we have landed somewhere else other than, like, other moons, so to say, other than our own moon. So it is a very, and in terms of gas giant distance, this is the furthest we have sent. It had 6 instruments, and it was very, very successful in terms of figuring out the atmosphere. And before this, like, okay, we can understand how things work in cryogenic temperature, but do we understand how cryogenic things work in cold temperatures, in a thick atmosphere, in a low gravity environment? So that is the reason why it had cameras, so we can actually see how pebbles are working, how wind flows are there, and it had many instruments to figure that part, like what kind of wind force we are talking about. So Huygens were also successful, but it was not classified as, like, glowing success. The orbiter was more successful. This was like partial success. Then we come to the end part of it. Now, NASA realized that they could just leave the orbiter and it will keep working as long as the RTGs keep working, equipments keep working. But they realized against that simply because there was a risk of contamination because of how the system is, the gas giant is. Its orbit is not stable simply because there are so many big, huge moons that they can disturb your orbit, and this will sooner or later will end up hitting something else, and there is a very good chance it could be the moon. And given the fact that we just absolutely confirmed that there is a liquids in there, we do not want to contaminate it. Given the fact that it may have a microbe from Earth, on top of that it actually has radioactive material, we do not want to dump that. So risk of contamination was so high that it was like, dumping it into the Saturn is the guaranteed way. However, doing that was not only like, okay, we're gonna protect against basically sort of future contamination. It was also that because we are compromising the whole spacecraft, we can do extreme things which no other spacecraft will. Basically, they've started to fly closer and closer and closer and closer to Saturn's system, to such a point where it started to dive between Ring and Saturn. It started to dive between them. Every orbit, like they had a profile figured in such a way that it will keep starting to get closer and closer and closer. So it actually, even in its last moment, it gave much more refined data, much more close, close calls for the whole system. So it was a very calculated decision. It was not like, okay, just for decontamination. No, it's like it also yielded a lot of thick data because of that. And the end of mission happened in 15 September 2017. Now, when I'm specifying this, you have to understand this. The main problem was the boom. The long antenna that you see kind of structure, it's actually magnetometers. And because they did not have the way of disconnecting the magnetometer, the system was having hard time pointing its antenna to Earth. Now, it went very deep into the atmosphere. From mathematical simulation, they know it went at least 5-10 minutes after the signal was lost. Because the primary thing they thought of is like, the antenna was moved out of position, because thrusters are small thrusters. It's like, 1 Newton and all that. And they could not just keep fighting against thicker and thicker. If they could have dislodged the magnetometer, they would have got another 5-10 minutes of extra data. So that would have been amazing. But again, it was not intended for that. So it had a glorious end, and it was a very successful, collaborative, and exposing kind of thing. Like, one thing to say, oh, mathematically we think there should be water inside, and another thing like, okay, we are going through the water, so it's technically swam through the water. Yeah, this is the only thing that did that. So it had an amazing mission. It had an amazing end, and I would urge you to watch the whole timeline. NASA provides surprisingly amazing detailed timeline missions where you can see how things unfolded, because we sometimes kind of lose focus, because you have to understand this. This kind of mission took like a person's whole career before this is over. So it is not something like, okay, I'm gonna start and it's gonna be over today. No, you're gonna start, your career will be over, the mission still might keep going. So this was my presentation on Cassini-Huygens mission. I hope you liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I'd urge you to press dislike, press it twice to show me extra disappointment, and please leave a comment, because I try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.